To walk through my solution for the formative that we did this week on the trigonometry, mostly on the trigonometric functions and just a tiny little bit on radicals. So the first question is meant to be quite simple. We're really just considering this angle alpha and then writing down all 6 of the trigonometric ratios. So this is really an assessment of whether or not you know the names of the trigonometric ratios and actually which 2 sides you use and which one is the numerator and which one is the denominator. And then also if you understand what I mean when I said using proper function notation, remember sine, cosine, tangent, cosecant, secant, and cotangent, those are all functions, and they take an argument, which is an angle. So we use function notation just as I've done here. We write the word sin, which is short for sine, of course, open parentheses, we put our input right there, alpha, and then close the parentheses. So this is kind of like writing f of x, but instead I'm writing sine of theta, or I'm sorry, sine of alpha. The next problem is really just computing what alpha is equal to. So we're looking here if you know how to use the inverse trigonometric functions, and that's what we mean when we put this little -1 here. So students are new to this idea of inverse functions and also to this notation, which is a little bit unfortunate because, of course, we use an exponent of -1 to mean other things. But here, when we see sine to the power of -1 or cosine to the power of -1, we mean the inverse sine and the inverse cosine. And they're inverses because instead of, like sine takes an angle and gives a trig ratio, the inverse sine takes a trigonometric ratio and gives you an angle. So it does the inverse of what the sine function does. And I said to do it in 2 different ways, which means really just use 2 different trig functions, or I should say inverse trig functions, as I've done here, with their appropriate ratios, which I got straight from the triangle, and really just plug it into your calculator and then round to the nearest tenth. Make sure you know what the tenths place is, because a lot of people rounded to the nearest hundredth in this problem, and so remember that first place after the decimal point is the tenths place. And moving forward here, we've got a triangle, and we're asked to find all the missing side lengths and angles. Well, and there's only 3. We're given 1 angle and 1 side length, and it's a right triangle, of course. And we're left to find the missing angle and then the 2 missing side lengths, and we're also told to round to the nearest tenth. So on this problem, I took the easy route, and I just used this simple relationship to find angle A, which is to say that these 2 angles in the right triangle, the non-right angle in the right triangle, those 2 angles sum to 90 degrees. And I've just used that information to calculate angle A, which is 28 degrees. Now, I didn't put 28.0, I put 28 degrees, and I thought about that a little bit, but this is exactly 28 degrees. So if I write 28 like that, in this case, I meant it to mean exactly 28 degrees, which is to say 28.0000 with an infinite number of zeros after that decimal point. From here, I decided that I would use the tangent of the angle I just found, and in order to find this missing side length. So the tangent of 28 degrees is the opposite over the adjacent side, so I've composed that ratio here, and then just simply rearranged my equation, plugged it into my calculator to get BC. And again, rounding to the nearest tenth, even if the tenths place has a 0 in it, we still report that. And I labeled my diagram here with the appropriate units. And then finally, there's a lot of ways to go about this, but I chose to use Pythagorean's theorem to find the missing third side, my hypotenuse, which is 25.6 to the nearest tenth. And there's a lot of different ways to approach this problem, and all of them will give you the same answers. So, and finally, the last problem on the first side, number 4, it was a little bit tricky, but I think this is a really straightforward solution here. What I did was first I just labeled this triangle, or I labeled all the vertices, A, B, C, and A, B, D. So I have my vertices labeled so I can kind of reference those in my solution. And I figured also when I'm looking at this, in order to get to x, I'm going to have to start with this side here, the hypotenuse of triangle ABC. And so if I use the sine of 60 degrees, I would be able to solve for this long side, which is the hypotenuse of my second triangle, triangle ABD. With and again, this is a 60-degree angle. So if I use the cosine, then I could just do adjacent over this hypotenuse to get to the value x that I'm looking for. So before I'm asked for an exact solution, and I'm also given this clue about rationalizing any denominators. And so those are clues that I'm going to have probably a square root in my solution because I'm rationalizing, and also when it's exact, we're going to leave it in a fraction form. I'm not going to write 2/3 as a decimal because any decimal that I try to write is going to be an approximation of the exact value of 2/3. So again, if you're writing a number exactly, you will likely have a fraction and maybe an irrational component like a square root, which is what happens in this problem. So again, you got to pick up on those clues. And here's what I did. I used the first triangle and I composed the sine ratio to get to side AB, and then I solved for AB. And then over here, I used the cosine ratio of 60 degrees to get to x. And that also involved side AB, incidentally, which is helpful. Because now when I solve for x, I get this. And then I can substitute from my first relationship into here. And I get this relationship here. X is equal to 9 sine 60 cosine 60. And surely I could just plug that into my calculator and I would get a decimal approximation of x that's pretty darn precise, but not exact. So instead, I remember the special right triangle 30, 60, 90, and I just wrote it here for my reference. And the short side has a length of 1, and the hypotenuse a length of 2, and that makes the long leg have a length of square root of 3. And this is good to commit to memory. And the more you use it, the more comfortable you are with it. And of course, I could scale these up. I could multiply all three of these sides by a factor, and the relationship would still hold. But in order to compute the sine and the cosine, I can just use this triangle because they're the same these are all 30, 60, 90 triangles. So the sine and the cosine and the tangent, all the trig ratios are going to end up being the same when I divide, because any scale factor between the two sides will just cancel out. So what I've done here is the sine of 60 degrees is just, here's my 60 degrees, opposite over hypotenuse. It's just this, square root of 3 over 2. And the cosine of 60 degrees is just 1/2. That's the adjacent over the hypotenuse. So I'm just taking this relationship and just substituting in my trig ratios. And then I can do a little bit of simplification, and I come out with this solution. And that is the exact side length x. The next video, I will discuss the other side of this formative.